In this video, we're going to talk about angular acceleration. This is the material on chapter 7 on the lecture notes from page 121 to 127. Let's start with the definition of angular acceleration. To find the angular acceleration of some reference frame g in F, it is defined as the derivative of the angular velocity of g in F with respect to the F frame. So let's look at the example. We have an aircraft that's pitching up, and a propeller at the front of this aircraft is rotating with the angular velocity of omega. So theta here is the pitch angle, and omega is the angular rate of the propeller. Let's assume that theta dot, theta double dot, and omega dot are non-zero. So to find the angular acceleration of the propeller relative to the inertial frame, let's mark it a F. What do we need? So first, of course, we need to define reference frames. We have F1, F2, and F3. And this is the inertial frame that is fixed. We also have another reference frame. G1, G2, and G3 that is rotating with the aircraft. So let's write down the definition of angular acceleration first. So in order to find the angular acceleration of the propeller in the F frame, we need to find the derivative of the angular velocity of the propeller in the F frame. And the derivative is taken in the F frame. So first thing we need is to find the angular velocity of the propeller in the F frame. So we know that the angular velocity of the propeller in the F frame can be decomposed by the angular velocity of the aircraft and the angular velocity of the propeller relative to that aircraft. So essentially, we have broken down the angular velocity of the propeller into two simple rotations. One is the rotation of the aircraft, which is the reference frame g in the F frame. And the second is the angular velocity of the propeller relative to that aircraft. So we know the angular velocity of the g frame or the aircraft relative to F is theta dot. That's the angular rate in the direction of G3. And we also know that G3 has the same direction as F3. So those two expressions are the same. And the angular velocity of the propeller in the G frame is simply the angular rate multiplied by the axis of rotation, which is G1. So we have expression of the angular velocity of the propeller in the F frame as in theta dot G3 plus omega G1. And another expression which is equivalent is theta dot F3 plus omega G1. Now let's take the derivative and find the angular acceleration of the propeller in the F frame. So we replace the angular velocity of the propeller with the expression we just found, either the theta dot F3 or the theta dot G3 plus the omega G1 term. Okay, so for here, I will choose theta dot F3 plus omega G1 simply because we're taking the derivative in the f-frame, and having the vector expressed in the f-frame simplifies the derivative. So now we have the derivative expressed in two different reference frames. So we will split the derivative and apply BKE as necessary. So for the first term, we have f3 hat, and we're taking derivative in the f-frame. So the derivative is simply theta double dot in the f3 direction. But for the second term, we have g1 hat, but we're taking derivative relative to f. So we need to apply BKE. Okay, again, notice that if we write for expansion of the BKE, we have the z vector expressed as omega g1 hat. We have g, which is consistent here, and we have the f, which are consistent as well. And we know theta double dot f3 plus, if we're taking derivative of omega g1 in the g reference frame, we have omega dot g1 hat. And we know the angular velocity of g in f, as we have found earlier, is theta dot g3 or theta dot f3, because the other term of the cross product is in the g frame. So we will use theta dot g3 as the expression for omega g in f. So now we have expression for the angular acceleration of the blade relative, or the propeller relative to the f-frame. Notice some properties that we have for the angular velocity. Earlier we said if we want to find the angular velocity of the propeller in the f-frame, we can decompose that into two simple rotations. Now you might wonder, does that hold the same for angular acceleration? And the answer is no. These two are not the same. Let's see the proof. So to find the angular acceleration of g in f, we need to take the derivative of the angular velocity of g in f. And we know that angular velocity of g in f from earlier is theta dot g3, or we have g3 hat equal to f3. This can also be written as theta dot f3. So we have the angular acceleration of g in f as in theta double dot f3. And what about the angular acceleration of the propeller in the g frame? Okay, follow the definition. We are taking the derivative of the angular velocity of the propeller in the g frame and relative to the g frame. we know the angular velocity of the propeller in the G-frame is simply omega G1, which gives us the expression for the angular velocity of the propeller in the G-frame as omega dot G1. Okay, notice that if we just simply add these two terms, we're not going to get the angular velocity of the propeller in the F-frame. So if I were to copy down the expressions I had for angular acceleration of the propeller in the F-frame, well, we can see clearly these two are not the same. So that we have angular velocity of the propeller in the F-frame does not equal to the angular velocity of G in F plus angular velocity of the propeller in the G-frame.